Yay! All right. Starting to look like a Friday instead of a Monday. Okay, example 4. We are going to be finding, if you look at part B ultimately, the derivative of f inverse at 2. And the function we have here is f of x equals 2/5 x to the 5th plus 1/3 x cubed plus 3x plus 2. So the two ways that we could set about trying to find the derivative of the inverse is, number one, we could let f of x be x and let x become y, and then we can solve for y to get the inverse function, and then simply take the derivative and plug in a 2. But how's that going to work? Yeah, it's not going to work at all. So rather, if we can begin with the end in mind and work backwards, and here's kind of the key, as I mentioned yesterday, to every inverse problem. You need to find the corresponding point. So on the function f inverse, and I like to do it like this, I write it as an ordered pair. There is an input of 2 and an output of question mark. On the graph of f inverse, there's a point 2 comma something, which means on function f, the corresponding point would be something comma 2, right? And all I got to do then is figure out, with my given function f of x, what do I plug in for x? What input do I use to get an output of 2? Sometimes it might come down to trial and error. If you're expected to find it by trial and error, it's going to be something relatively easy, like a 0, a 1, or a -1. But a lot of the times, there's a clue. Like part A says to find f of 0. Sometimes it might say this. Find, it might say find f inverse of f of 0. Something like that. That's composition, but remember the output on f of 0 is the input on f inverse, and then prime. So there's going to be some kind of hint. All right, well, let's go ahead and plug in a 0 for x and see what we get on function f. We get 0 plus 0 plus 0 plus 2. There's the hint, right? So we kind of found it. On function f, there's an ordered pair called 0, comma 2. Use blue. Which means on f inverse, there's a corresponding point called 2, comma 0. And here's what I know then, without even doing any other calculus. F inverse prime of 2 is 1 over f prime of 0. And for what it's worth, f prime of 0 is 1 over f inverse prime of 2. Inverse functions at corresponding inputs have reciprocal derivatives, right? So this is going to be our plan of attack. Since I couldn't find the equation for f inverse to take the derivative, I'm going to take the derivative of the function that I was given, f, plug in a 0 to the derivative, and then take its reciprocal. That's what we're going to do. All right, so here we go. F of x is given, f prime of x. It's just a little power rule, right? 2/5 times 5 is 2, so we get 2x to the 4th, plus 3 times a third is 1. We get x to the 2nd, plus 3. That was easy. Didn't even break a sweat. Now we plug in a what? Do we plug in a 2 or a 0? Very good. The 2 is the input on f inverse. We got to plug in the input for f, which is 0, the corresponding input. F prime of 0 is 3. Okay, so here we go. F inverse prime of 2 is 1 over f prime of 0, which is 1 over 3. And we have our answer, 1/3. The answer is 1/3. Now, this one didn't ask us to determine if our function was 1-to-1, but it's irrelevant here. Even if there was more than one output, you would be given a value of x to compute so that there was only one point associated with it. All right? We could probably prove that it is 1-to-1, very similar to what we did yesterday, right? If you take this derivative here, what do you know about that derivative? It's always what? It's always positive, right? So our function f of x, which is continuous because it's a polynomial, is monotonic increasing. So even though it was a 5th degree polynomial, it could have had as many as 4 turning points and therefore failed the horizontal line test. It did not. It was monotonic increasing. So for a continuous function, which bless you means it was 1-to-1. All right. Look at this. It says sometimes we are handed all the ingredients to the recipe given to us in pre-measured bowls, and all we have to do is dump them in and stir. What does that have to do with calculus? Oh, it's an analogy or a very short allegory. Let's see. Example 5. If m of n of x equals x, which equals n of m of x, what does that mean regarding m and n? Yeah, m and n are inverses. So we know at corresponding points they're going to have reciprocal slopes. They're going to undo each other's work. Make a good team, maybe. If m of 5 is negative 9 and m prime of 5 is negative 8/11, then find n prime of negative 9. All right. I guess these are analogous to the pre-measured bowls, but we need the bowl to dump everything into. We need our template. So begin with the end in mind, right, and work backwards. We need to find the slope of n at negative 9. That means on function n, negative 9 is an input, yes? And it's going to have some unknown output, which means on the inverse of n, which we just said was m, negative 9 is the output, and we need to find the input, right? So I was only given information about m. So notice, if you look at the first piece given, m of 5 equals negative 9, that means negative 9 is the output, and the input I'm looking for is handed to me right there. I just got to know what I'm looking for. It's 5. So for what it's worth, the y value then on the inverse is 5. But 5 is the magical ingredient to this recipe. That's what I was looking for. Because now n prime of negative 9 is 1 over m prime of what? 5, right? Inverse functions at corresponding inputs, negative 9 and 5, have reciprocal slopes. Well, gosh, now I need to go out and find m prime of 5. Where does a fella get that? It was given to me. So I just plug it in, and I get 1 over negative 8/11, which is the ugly version of the right answer, right? If you're given a fraction, the easiest way to take its reciprocal is just to do what with it? Flip it, yeah. Or do this and then say state change flip. Voila, there you go. So really, you were kind of staring at the answer the whole time. It just ended up being the reciprocal of one of those numbers. You just had to know which one to take the reciprocal of. Will I give you a problem this easy? Possibly. Will College Board give you a problem this easy? Yes. The only thing is they may give you other ingredients that are not part of the recipe, right? Like you have butter and sugar, and they may give you like a pile of dirt and a box of rocks, right? Unless you're making a dirt rock cake, you would probably not want to choose those. So there's going to be other things, and you have to know that they're not part of what you want. So that's why it's important to say, okay, begin with the end in mind. Negative 9 is the output, so it's the output for the information I'm given. I need to find the input, and then I need the derivative of that input and flip it. And where can you go find other problems like that with distracting ingredients that you won't be using? In the worksheet. Yeah, in the worksheet. Okay, example 6. Oh boy, this looks like it's a perspective, like free response type style, where I can give you a chart or a table of values and ask you all kinds of things, like IVT questions maybe. Selected values of a 1-to-1 differentiable function f and g. 1-to-1, meaning they're invertible. They have inverses that are functions. Differentiable, meaning not only the derivative exists, but they're also what? Continuous, right. F of g and f prime are given in the table above. If f of g of x equals x, which equals g of f of x, again, that's a pretty common way to present to you two inverse functions. F of g are inverses of each other. Find g prime of negative 3. Find g prime of negative 3. I'll give you a minute to do that on your own, because you got a lot of distracting ingredients now. But the right ingredients are there. G prime of negative 3. Good. I see some of y'all actually writing down things that I wrote down. Good. It helps to have like a standardized approach to these problems. All right, so what I would do again is, if negative 3 is an input on G prime, it's also an input on G, right? A function and its derivative have the same input. So on the G function, there's a point negative 3 comma something, and on the F function, its inverse, there's a point called something comma negative 3. So that's your first goal, is to find what input on F gives you a negative 3. So if you look in the F column, you're looking for an output of negative 3. There it is. You're not looking for the input of negative 3. Notice that is there. So for the person who doesn't really know what they're doing, they think F of negative 3 is 4. And that is correct, but that's not what we're looking for. We're looking for the output of negative 3, not the input for negative 3. So what is the input on F that gives us negative 3 for the output? 7. Yeah, that's not a difficult thing. You know what you're looking for. It's pretty easy to find. Yeah, so now, is that the only way to find it? No. In this case, you could have found it the other way, right? If you know negative 3 is an input on G prime, I don't have the G prime column, but I do have a G column, and notice there is a negative 3 input listed, and its output is 7. So in this case, there were two ways to find it. Typically, we're not going to be able to find it that way. We're going to have to come in through the back channel here of F looking for its input. So it's 7. So now what I know then, since there is no G prime column, I know I have to go through F prime. So G prime of negative 3 is 1 over F prime of what? 7. Yeah. And F prime of 7 now we can get from the column to be 2. There you go. Now notice there's also an F prime of negative 3. So guess what an answer choice would be on the test as well? 1, 6 would be another answer choice. So you have to know exactly what you're looking for. But when you know what you're looking for, it's really easy. It doesn't require a whole lot of work. Even for problems like this where we have to find our own derivative, it's not that difficult, okay? So inverse functions at corresponding points have reciprocal slopes, or to make it more calculus-y, inverse function at corresponding inputs have reciprocal derivative values. Yeah, very good. All right, any questions on that idea? All right, so now we're going to look at specific inverse functions, okay? Very specific type of inverse functions, namely inverse trig functions. And if you remember for pre-cal, we spent a whole unit on this. We're not going to spend a whole unit going over this, but I'm going to review a couple of them. The first one we're going to look at is inverse sine. So very, very, very quickly, if you look at the graph of sine of x, or Sahala as we called it, right? Sahala is not 1-to-1, is it? Not by any stretch of the imagination. It fails the vertical line test. I mean, the horizontal line test pretty miserably. It does pass the vertical line test. So remember what we did. We said there were hopes for functions like sine that were not 1-to-1. If we could all agree on a value or an interval, that is, to restrict this function so that it were 1-to-1 on that interval, then I could reflect that piece of the graph only across the line y equals x and get the graph of the inverse function. But we would all have to agree on the interval to choose. And so the criteria was, all right, if I'm going to restrict this to an interval, sine of x, I need to restrict it, first of all, to an interval that includes all the y values that the graph takes on. This graph takes on all the y values from -1 to 1, right? So I need to restrict it essentially from a high point to a low point, or a low point to a high point. So that was the first criteria. Got to contain all the y values. The next piece of criteria was it had to be a 1-to-1 interval. So I can't go from one high point to the next high point, because as soon as I go down and back up, or up and back down, it's not 1-to-1. So I need to look for a 1-to-1 interval. And the third criteria was it had to be a convenient interval. Convenient interval meaning relatively close to x equals 0. And so last year, I think we all voted on it, right? We all decided that the interval that we were going to use was the interval from -pi/2 to pi/2, right? That's going to be from this low value to that high value. It's convenient because it lives near 0. In fact, it passes through 0. There were about 5 people, if I remember, and I don't know if it was anyone in this class, they voted for this interval. And I was like, that's not bad, but it actually is disconnected from the y-axis. So I'm going to go ahead and straddle it. And then there was that one person, and I don't think he goes to school here anymore, and he voted for that interval, right? He was a negative person. He liked negative intervals. So anyway, I'm making all that up. That was decided well in advance of our existence, right? So if we take this convenient 1-to-1 interval right here from -pi/2 to pi/2, and you reflect that and that alone across the line y equals x, guess what you get? You get the graph of inverse sine, which is going to look like this. Something like that. All right, and if you drew the line y equals x, it would be symmetrical across that. So I know that graph is getting kind of congested now, but the x values from -pi/2 to pi/2 become the y values, right? We called that the principal value range, or eventually just the range, and then the y values of -1 to 1 became the domain. So here's what the graph looked like. The dotted line parts are the parts that we did not use. So here became the function inverse sine of x. It starts right there at -1, -pi/2. It's a monotonic increasing function, and it goes to the point 1, pi/2. So the domain of inverse sine was -1 to 1, the old range of sine. And the range, or the principal value range, is -pi/2 to pi/2. So that is the function inverse sine. We call inverse sine one of two names. That is the inverse sine name, or recall, because inverse sine can be inherently confusing with the reciprocal of sine. Its other name was arc sine of x. Okay, arc meaning it's related to the radian. Well, once we have the function and we have its graph, guess what? We can start talking about, I wonder how fast that graph is changing right there at that point. Or if I can model some real-world behavior by an inverse sine function, I want to know how fast that quantity is changing at that moment. So now we need to start getting into the calculus part. I need to be able to find the derivative function for inverse sine of x. And Galileo also was not able to do this, poor guy. But we're going to be able to do it. In fact, we're going to be able to derive it. And that's going to be pretty exciting. But before we do that, let's meet the other function. Inverse sine of x, the graph, believe it or not, you don't even have to memorize what the inverse sine function looks like. There are 6 inverse trig function graphs. The only inverse trig function graph you're responsible for memorizing is inverse tangent. Okay? Or arctangent. This one is very important. This one will show up again later in the year when we do L'Hopital's rule and improper integrals. It has horizontal tangent lines at pi/2 and -pi/2. Those are the old vertical asymptotes of tangent. They become the horizontal asymptotes. It's a monotonic increasing function. It kind of looks like the cube root of x, except it's bounded between -pi/2 to pi/2, and it does not go vertical at the origin. These are important because they have end behavior. The domain is all real numbers. What is the limit as x goes to infinity of arctangent? I think we've already had this year. Pi/2, yeah, and if you go out to the left, it's -pi/2. All right, so that's the only inverse trig function you're responsible for knowing, but you do have to know the derivatives of all 6 inverse trigs, all right? And for what it's worth, there's inverse secant. Hello, inverse secant. Bye, inverse secant. Ooh. distant. So here we are in example 7. We are going to derive the derivative, appropriately enough, for arc sine of x. All right? So here's what the question says. If y equals arc sine of x, I tend to use arc sine instead of inverse sine, but I will use inverse sine occasionally. Find dy dx. Okay, I'll give you about a minute to find it on your own. Don't forget to look under every rock and stone. Leave none unturned. Find it. Some of y'all are going to be smart and you're going to find it by scrolling down. That takes all the fun out of the search. Jessica already found it. Okay, seriously, I mean, if you just take the derivative of the left, that's easy. That's dy dx. But now you're taking the derivative of the right with respect to x, and that's where you're like, I don't know. I'm going to guess arc, the derivative of sine is cosine, so maybe the derivative of arc sine is arc cosine, right? That would be wrong, and you could verify that with some test values. So guess what? This is not going to work. I'm going to show you how we can derive it. You don't want to have to derive it every time, so you're going to want to memorize it, but it's kind of fun to see where things come from. I don't know how to take the derivative of arc sine, true, but I do know how to take the derivative of sine, right? So even though this one is explicitly solved for y in terms of x, which is kind of nice, I'm going to go ahead and take the sine of both sides, sine of arc sine of x, and I'm going to get it out of explicit form. So I get sine on the left, and on the right, what is sine of arc sine of x? It's just x. Now, I know how to take the derivative of sine, and I also know how to take the derivative how? Implicitly. So that's what we're going to do. We're going to take the derivative of both sides now with respect to x, using implicit differentiation. Sweet. Rely on things that you already know and build upon them. All right, what's the derivative of sine of blob? Cosine of blob. And in this case, the blob is y. Times the chain rule, the derivative of y with respect to x. Don't forget that. You have one y in the entire equation, so you're going to have one dy dx. And on the right side, the derivative of x is dx dx, also known as 1. Now I got to solve for dy dx. This is shaping up to be pretty easy. It's 1 over cosine. 1 over cosine. Another name for 1 over cosine is sexy. Or secant of y, sorry. 1 over cosine is sexy. 1 over cosine of y is secant of y. So there you go. We have it. There you go. The derivative of arc sine of x is secant of y. How satisfying is that? Not very. Why? Yeah, we started off with an explicit function that required only an input of x. Now you're telling me if I want to find the derivative, now I need to know the y value? Oh, bother, said Pooh. So what we're going to do is we're going to put that back in terms of x. And this requires a little bit of cool stuff from pre-cal. Yeah. So let's come back over here and look at what we started with. Arc sine of x. Remember, the input for all of your trig functions are what? Angles or ratios? Right, ratios. We take the inverse trig of a ratio, or the arc trig of a ratio, to find an angle. We take the trig of an angle to find a ratio. So x is a ratio. Doesn't look like a ratio. How can we make it look more ratio-esque? X over x? That would be cool, right? But that would be wrong. We want to keep it the same. X over 1. Yeah, that looks more like a ratio. Now, it's not an arbitrary ratio. It's the sine ratio, yes? So if I take the arc sine of x, it's going to give me some angle theta. Don't know what it is. So let's go ahead and go into the first quadrant and draw just a generic reference triangle whose reference angle is theta. We drop a perp, right? Drop a perp. And now I'm going to label the two sides that I'm given. They're going to be in terms of x, but that's all right. Sine, remember, in terms of x, y, and r, was y over r. Or in terms of SOHCAHTOA, it was opposite over hypotenuse. So from the reference angle, the opposite side is x, the hypotenuse is 1. Or y over r, however you want to do it. And of course, once you have two of three sides of a right triangle, you can always find the third side by the good old P theorem. Yeah, the Pythagorean theorem. So if you want to call this a temporarily, a squared plus x squared equals 1 squared. If you solve for a, you get the square root of 1 minus x squared. And of course, we want the positive version. We don't know if it's going to be positive or negative, so we'll just choose the positive version, 1 minus x squared. If you choose the positive, you're going to stay within the PVR of arc sine. All of your inverse trig functions have quadrant 1 in their domain and range. Okay, so now that we have all three sides, don't we have all 6 trig ratios in terms of x, of course? Yeah, we do. So now, if we let that angle equal y, right, that's what y is. Y is the angle. It says the derivative of y with respect to x is just the secant of y, which is the secant of the angle theta. Well, what is the secant in terms of x, y, and r? Secant of theta is the reciprocal of cosine, so it's r over x. It's the hypotenuse over the horizontal, or the hypotenuse over the adjacent. And that's going to be 1 over the square root of 1 minus x squared. And that makes me feel a lot better. Because now I know when y equals arc sine of x, and I have x, I can just plug it in here and get the derivative, and I don't need to find y ever. So the derivative of arc sine of x is 1 over the square root of 1 minus x squared. And that we have to memorize. All right? So here we go, without looking. The derivative of inverse sine of x is? Good. Yes, some are faster than others. You'll get speed with practice. But there it is, the square root of 1 over 1 minus x squared. We got it. Now, you can do the exact same thing in a very similar fashion to derive the derivative of the other 5 inverse trig functions. I'm going to leave that for you to do in the privacy of your own home over the weekend if you choose. Okay? We're going to jump straight down to the results of your weekend private practice. Okay? Here they are. All 6 inverse trig functions, starting with the 3 main ones, if you want to call them the main ones. They're the ones that don't have cos in front of them. There's 3 trig functions, remember, and 3 co-functions for those 3 trig functions. Same thing with the inverse trig. So the derivative of arc sine of x or inverse sine of x, as we just said, is 1 over the square root of 1 minus x squared. The derivative of arctangent of x is 1 over no radical, just 1 plus x squared. Or, of course, x squared plus 1, commutative. No radical, but still has a 1 and still has an x squared, right? Arcsecant of x, kind of the weirdo. It's 1 over the absolute value of x outside the radical, and then kind of like sine, it has a radical, but instead of 1 minus x squared, it's x squared minus 1. All right? So what do they all have in common? They're all 1 over, and they all have x squared and 1. Arcsine and arcsecant have radicals. Arctangent does not. 1 over 1 plus x squared. Arcsine is number minus function. That's going to be kind of a nice way to memorize it moving forward. And arcsecant is function minus number. And it also has the weird absolute value of x out front. So I'm not sure if there's a better way to memorize them other than just practice and rote. Yeah. You would have to call the absolute value of x, of course, the square root of x squared. And then you could bring it under here because it's both the square root. So you could call it, I mean, if you want, I wouldn't memorize that version, but it would be the square root of x to the 4th minus x squared. That's another version of it, yeah. But that puts it in such a dramatically different version from the others. And that's not how, like, multiple choice answers are going to be. So that's fine if you want to memorize that in addition to, but it's just another version of this. Now here's the cool part. If you memorize the 3 non-arc co's, the 3 arc co's come for free. So like I promised you earlier, if it has a co in the name, whether it's cosine or arc cosine, they're going to be what type of derivatives? Negative, and they will be. And that is the only difference for the inverse co's. They are just the opposite of the non-co's. That's pretty sweet, right? So because arc sine was 1 over the square root of 1 minus x squared, arc cosine is just negative 1 over the square root of 1 minus x squared. Piece of cake. And because arc tangent was 1 over 1 plus x squared, arc cotangent is negative 1 over 1 plus x squared. And same thing for arc secant. It's just a negative in the top. The bottom is exactly the same. Get 3 for free. Pretty easy, right? And they're all negative because they all have co's in it. Nice. And memorize as you go. Don't memorize all the night before the AP exam. Memorize as you go. Makes it easy. Okay. Any questions on those? If you come up with some like fancy way to memorize them, share with us. I think if you use them, they're going to kind of just become a part of you, and you're not going to have to force yourself to memorize them. If Quizlets work for you, maybe make a Quizlet app or something. I don't know. Let's try it out. Example 8. Find the equation of the tangent line to the graph of inverse cotangent at x equals 1. Now that is inverse cotangent or arc cotangent, not the reciprocal of cotangent. That would be tangent. So we don't need to know what the graph looks like. We just need to be able to find the equation of the tangent line. So what do we need for the equation of a line? We need a point and a slope. Yeah. So the point is going to be 1, comma, and y is the same as f, right? You plug it in, and the y value is inverse cotangent of 1. Now that's an exact answer, but we could do better than that. Let's evaluate inverse cotangent of 1. The best way to help yourself evaluate it is instead of just saying inverse cotangent of 1, say it like this. Cotangent of what quadrant 1 angle? When in doubt what the PVR is, just go with quadrant 1 because it's common to all of them. What angle in quadrant 1 has a cotangent value of 1? Pi fourths, right? Remember, pi fourths is square root of 2 halves, square root of 2 halves. So x over y, you get 1. So that is pi fourths. You'll get an angle, pi fourths. Now the slope. Slope at that point. Slope at the point, that's the derivative. So we have y, we need the derivative. That's dy dx. So here's what I know. It's inverse cotangent. So I know it's a negative 1 over something because it's co. And now it's the opposite of tangent. Tangent was 1 plus x squared. So there's the derivative. And now I'll just plug in my 1, the same input. And I need to notate that. So remember, in Leibniz form, you put the evaluation bar, the when bar, and in this case, you could just put x equals 1 down there. So don't take that for granted because you'll lose points. Now we plug it in, we get negative 1 over 2, right? Negative 1/2. And now we have our ingredients. Now we just need to assemble it. So the equation of the line in Taylor form is y equals the y value of pi fourths, good, plus the slope, which is minus 1/2, times x minus 1. Ta-done. That's it. Now let's do something else here. Let's go ahead and put this into general form, because this would make a good multiple choice question. And I think I mentioned when we went over the test that even though we write all of our line equations using Taylor form, sometimes on a multiple choice, especially if there's a fraction, College Board will like to put it in general form. So the first thing you want to do to get it in general form is to clear out the fractions. So we're going to multiply both sides by the LCM of all your denominators, kind of like lick 'em over lick 'em. You have a 2 in the denominator and a 4. Which one is their least common multiple? The smallest number that they both go into. 4. 2 would be their greatest common factor. 4 would be their LCM. So you multiply the left by 4 and the right by 4. And notice I put parentheses on the right. That's real math. You get 4y on this side, and now when you distribute, you're going to get a pi minus, and 4 times a half is 2. So we're ending up with a negative 2 here, which then we have to distribute. Can we do that in one line? Sure. So a negative 2 times x is a negative 2x, and a negative 2 times negative 1 is a positive 2. So once you get rid of the fractions, the general form typically is like this. It's of the form ax plus by equals c, and a, b, and c are typically integers. Okay, they're not fractions. So all you have to do now is get your x's and y on the same side. I'll add 2x to both sides, and we get 2x plus 4y, and in this case we get pi plus 2. They're both constants, but they're not like terms, so we'll just leave it as pi plus 2. Now, if you find that your signs are wrong, there's not an answer choice, if you just multiply everything through by negative 1, you get the other version of it. Now, I doubt that would be the case here, but sometimes if you have like a 2x minus 4y, it could be a negative 2x plus 4y just by multiplying both sides by a negative 1. They're both correct. Typically, we like to have as many positive terms as we can, more positive than negative terms. So in this case, the top one would be correct. All right, so that problem hinged upon our ability to find the derivative of inverse cotangent, which we now know. All right, so example 9, it says to differentiate. It's kind of like a rapid fire little thing here. So I'm going to let you give A and B a shot without me. And I'll walk around and see how you're doing, and then we'll come back together here and see how you did. All of the rules now that we've learned, product, quotient, chain, power, they're all on the table. It's going to be a combination of methods now to take any derivative. Rewriting is still an important thing. Putting grouping symbols to help you see layers or factors, that's a good thing still. No, you don't put, because you got to be taking arc sine or something. Yeah. These from a long time ago. I put them in the wrong bin. There's your quiz from the other morning. All right, I'm looking around, seeing most of y'all are done with A, so I'm going to kind of go over it. If you think you got it, tune me out. If you want to check, go ahead and listen in. You have two terms, that's nice, so each term is kind of like its own separate problem. The derivative of 4x is just 4 by the power rule. And remember, this is the expressional verb format, so there's no dy dx equals. You don't put anything in front. You just, the derivative of the top line is, implied is, 4. And then now we have arc sine of blob. So this is the chain rule. The chain rule. The derivative of arc sine of blob is going to be 1 over the square root of 1 minus blob squared. Blob squared. Okay, because that's not an x anymore. and I'll just write the blob right there, and then times the chain rule, the derivative of the blob, which is 4x by the power rule. Now we'll go through and clean it up. The 4 is still a 4. Since that's 4x over 1, I can throw it into the numerator. It's a nice tidy place to put it. And then in the denominator, of course, since you have the parentheses, you know that 2x squared quantity squared is not 2x to the 4th, but rather 4x to the 4th. And that's your final answer. Don't then make the mistake of saying, oh, simplifying is one thing, but oversimplifying is another. Is the square root of 1 minus 4x to the 4th 1 minus 2x squared? No, those are terms, not factors, so that would make a great answer choice, though. So don't do that. This is about as good as it gets. If you wanted to get like a common denominator, you could, but this is it. There's your derivative. All right, letter B. Keep hitting that one. Little sledgehammers. Oh, you're already on part C. Wow. Yeah, that's it. Yep. Good. I put good. No, it carries through. Once you call it A there, you can call it A everywhere else. Yeah, no, when in doubt, do it again. But yeah, once you call it A there, that's why I said good. And you refer to A of T. Yeah, perfect. So, yep. Well, no, you're not doing the product rule. You can't take the derivative of both of them like that. That's not how it works. Okay, it's the derivative of this times this. So it's the product rule, right? So it's the derivative of that times, remember, this one goes along for the ride. You don't do anything with it the first term. And then plus x goes along for the ride times, and that's where you take the derivative of that. The second one on B here is probably worth a rewrite and some addition of some parentheses. Something like that. You have a product now of two variable functions, so this will be a product rule. And the square root of x, ultimately, you're going to have to take its derivative, so you'll need to write that, or at least think of it as x to the 1/2. Product rule, for some reason, again, the one most students want to kind of get it wrong right away. Derivative of the first times or the second, it doesn't work. Two factors means how many terms? 2, all right? So the derivative of x is 1 times the second we just rewrite, arctangent of, and you can put it as square root of x again here if you want, or leave it as x to the 1/2, it doesn't matter. Plus, now we rewrite x, and now it's time for the derivative of arctangent of blob. The derivative of arctangent of blob is 1 over 1 plus blob squared. And of course, what's the blob? It's the square root of x. Times the chain rule, the derivative of the blob. The derivative of x to the 1/2 is 1/2 times x to the negative 1/2 power. So that is just another factor in the second term. And that's it with the derivative. Calculus lines never last more than one line. Now it's just about kind of cleaning it up, bless you, and putting it in a more user-friendly format. You can combine x's here. You got x to the first in the front times x to the negative 1/2 in the back. And remember, when you're multiplying and the bases are the same, you don't eve the exponents. You what? Add them, right? You add them. So what is 1 minus 1/2? 1/2. So you're left with x to the 1/2. I'm going to call that the square root of x. I'm going to put it in the numerator. That combines those two highlighted. Now, I have a 1/2, so that's going to be a factor of 2 in the bottom. And then I have a quantity, so I'm going to put parentheses 1 plus. Now, the square root of x squared, is that just x, or is it the absolute value of x? No, it's not the absolute value, because remember, the absolute value would accept both positive and negative x's. This one doesn't accept negatives. So the square root of x squared is the absolute value. This is the square root of x quantity squared, so you could just put an x there. If it were this, the square root of x squared, that's where you'd want to put an absolute value there. Yes, Gorell, what did I do with both x's? Is that what you're asking? I combine those right there, off to the side. Yeah, and that's fine. X to the first times x to the negative 1/2. That's x to the 1/2, which is the square root of x. And then I just put that over 1 and threw it in the numerator. So there's kind of the nice cleaned up version. And now I guess the last one we'll get to for today, unless they don't come on and interrupt us with the announcements. I'll shrink that one down. This one here, you're dividing by 5. Would you use the Hody-High rule here? Yeah, just rewrite it. Dividing by 5 is the same as multiplying by 1/5. Now it's a constant multiple and it goes along for the ride. So you got arcsecant of sine of. I like to put parentheses around all my layers. And now you really have how many layers? 3. So you should have 3 factors in your chain rule, 3 links in the chain. So the derivative of 1/5 blob is just 1/5 times the derivative of the blob. Well, the derivative of the blob is arcsecant. The derivative of arcsecant is 1 over, it's not arccosecant, so it's just positive 1 over the absolute value of the blob times the square root of blob squared minus 1. And notice when I say blob, I put open receptacles. What is the blob that goes in there? Sine of 3x. Yeah, that whole thing. Sine of 3x. Sine of 3x. All right, times I go in a layer, and that's where I see sine of blob. So times the derivative of sine of blob is cosine of the blob. And then finally, the derivative of the blobbiest of blobs, the innermost blob, the derivative of 3x is 3. So now, putting it all together, cleaning it up, it looks like I'll have a 3 cosine of 3x in the numerator, because that's all over 1. I'll have a 5. Can I just drop the absolute values around the sine of 3x? No. The only time you could drop them is if what is inside is like already positive everywhere on its own. So if you had like an x squared plus 1 or an e to the x or something like that. But sine of 3x, you know, that still oscillates between negative 1 and 1. So we got to keep it. And then here we can say sine of 3x squared, if you want to write it in the condensed format, squared of 3x minus 1. All right. So that problem I made up just to practice taking the derivative. One year I decided, hey, let's go a little bit further, and I realized that the problem actually doesn't even exist. Why? Let me show you while he's talking. Weather report, weather report.
Would please rise for the Pledge of Allegiance.
If I use Papa Pid, pledge allegiance to the flag, the United States of America, to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Honor the Texas flag. I pledge allegiance to the Texas, one state, under God, one and indivisible. You can go, yeah.
Thank you. You guys have a great day.
Oh, will do. Okay. So, anyway, I wrote the Papa Pid out here with a 3x angle. Sine squared plus cosine squared is 1. So if you replace sine squared of 3x minus 1, it's equal to negative cosine squared, right? That's the same thing as the square root of negative 1 times the square root of cosine squared. What's the square root of negative 1?
We had great student support. However, some people brought some baby powder.
Yeah. So anyway, it doesn't exist. But we still could take